Welcome to the Lindamood-Bell radio podcast, where we explore topics in learning and literacy. I'm Dave Hungerford, and I first want to let educators know that you can attend one of our renowned teacher workshops. Nancy Bell and Pat and Phyllis Lindamood have pioneered programs to develop the sensory cognitive functions that underlie language and literacy skills. We want to help you teach your students to learn to their potential. That's why all of our workshops, like visualizing and verbalizing, seeing stars, and lips, are now available online. Plus, when you take an online workshop, the price of your complete kit is included. Find the workshop schedule at lindamoodbell.com. Today, I'm talking with Dr. Guinevere Eden, who directs the Center for the Study of Learning at the Georgetown University Medical Center. Welcome, and nice to have you here today.
Thank you for having me.
You're a neuroscientist, you study the brain, and you're also a renowned expert in reading. And I think a lot of people might not put those two fields together. Which came first for you, and how did they intersect?
Well, that's a very good question because, in fact, the field advanced very rapidly at a time when I was in my training. And, of course, when we train, we don't know what lies ahead of us. And one of the things that changes the course of research is the technology that's developed whilst we're doing our studies. And I was very fortunate in that I trained as a physiologist at the time for my undergraduate and my graduate degree. And I then came to America to learn how to do brain imaging. I went to the National Institutes of Health in Bethesda, Maryland. And when I arrived here with my one suitcase and a request to come back to Britain by the British government, I fortunately came at a time when functional magnetic resonance imaging had just been invented and was being developed, and was fortunate enough during my postdoctoral training to study dyslexia in adults with dyslexia using this very new technology. In fact, it was the very first fMRI study of dyslexia that was then published in Nature. And so to answer your question, what came first? I was trained as a physiologist. I was interested in understanding dyslexia, and my graduate work was looking at behavioral measures. So I measured pencil and paper tests. I was also interested in eye movement control at the time. And then when I finished that training, I wanted to come to America to learn how to do brain imaging. And there wasn't that much opportunity in Britain at the time. That's all changed. But at the time, there weren't that many places. And so I was very lucky to come to America to do that training. And where this then continued on is that this technique is non-invasive, which means that we were in the position to start studying the brains of children who are reading just fine and children who are struggling readers. And we basically extended the technology down to the study of children, as did many of our colleagues. And that really provides an opportunity to do not just neuroscience of reading, but educational neuroscience, where you're trying to bring together these disparate fields.
So in the early days of looking at the fMRIs of brains, was the focus trying to find a certain geography, a certain area that affected dyslexics, or that dyslexia would show up?
So the understanding of the brain basis of reading and reading difficulties was already quite well known from early studies in patients, adults who were reading just fine until they had a stroke. And then, because of their stroke, would lose the ability to read, and not just read generally, but very specifically. Some patients, depending on where their lesion was, would have difficulty in pronouncing words that they needed to sound out, like pseudo words, pretend words that follow the rules of English pronunciation, but you have to apply sound, grapheme, phoneme sound correspondent
like
rules.
A word attack test.
Like a word attack test, exactly. And then there are patients who could do that just fine, but they had difficulty with reading words that you have to remember, like yacht and so on, that aren't pronounceable. And these kinds of acquired dyslexias really gave the scientists already a good feel for how the brain is organized. There were models of reading with this idea that we have certain pathways where we use for sounding out words and others that we use for sight word recognition. But the imaging piece really became very important for dyslexia, because when you study adults with dyslexia and children with dyslexia, and it's a developmental condition, then you want to ask the question, is it the same circuitry? And the imaging work then began with adults who participated as volunteers in studies that utilized imaging techniques that weren't suitable for children. Positron emission tomography, you inject a radioactive tracer. The tracer is taken up in the bloodstream, it goes into your head, and it goes to those areas that in your brain that you are utilizing to do the task, which is what these brain imaging techniques rely on. But if you use something like positron emission tomography, you can't study children or healthy children. And so that technique was great in terms of visualizing the reading brain and looking at the brains of people with dyslexia. And there was a lot of work that was done in the 80s and 90s, early 90s, using that technique. But it was the functional MRI that allowed the scientists to then also ask the same question in children, because the fMRI technique doesn't use the injection of a tracer. And that's important because if you look at the brains of people who have dyslexia as adults, you don't quite know whether the differences that you may see between them and people who didn't struggle with reading are the differences that cause their reading problem or are the consequence of a lifetime struggling with reading and not having the same reading experience as their peers.
Well, the brain goes through many changes as we go through life, correct?
That's right. And so when you study the reading brain in children, you are looking at a very dynamic process, right? Their brains are already developing, and then you are overlaying on that development a skill acquisition that is quite long. It takes years to learn to read. And so there are two things going on. They are becoming experts at something. They're learning a new skill. It's sort of a training that results in changes in the brain. But then on top of that, you have other brain changes that occur outside of reading that are just driven through our normal neurobiological mechanisms and hormones and development. And those, of course, are intertwined, which also, again, makes it challenging to study the reading brain. And this is where, again, neuroscience has been very helpful because some studies in the last decade have focused on adults, comparing adults who have never learned to read with those who have learned to read, or those who didn't learn to read as children but then learned as adults, where you then essentially remove the developmental changes because you're just looking at adults. And what those studies have shown is that learning to read changes the brain. So we already knew that from children, but it sort of helps if you take the developmental portion out of it. And you can see that in adults when the brain is mature and it's not a reading brain, but then it trains to read and becomes a reading brain that's associated with significant functional and anatomical changes.
And I've heard you talk about how the reading act itself is not really a basic human brain activity. It has some artifice to it. Isn't that right?
Yeah. So the way to think of it is that our brain wasn't really designed to read. We do have skills in our brain. Our brain can do things that it can do from a very early age, from birth, and it suggests that these skills are hardwired. So, for example, if you look at the organization of the visual system develops and requires input for development, but it also has certain features that are clearly hardwired. That's been sort of an ongoing debate in neuroscience, how that works. But what we know for certain is there's nothing in the brain that's assigned to be the reading brain, because from evolutionary perspective, we haven't been reading for long enough. We've been reading, early signs of writing systems are somewhere between 4,000 and 6,000 years old, but that's not long enough for us to have an evolutionary pressure to develop with the advantage of becoming a skilled reader. So the way you think of reading is that it essentially is it's a cultural invention. We've only been using it really very actively in the last few hundred years. We go to school to formally learn how to read. And when the brain learns to read, it sort of looks around and has to take areas that can perform certain skills that make it amenable to reading. They have to be similar enough that they can do it, and they have to also be available, and they have to be open to change. And Stan DeHaan describes this as a process of neuronal recycling, which is a nice way to think about that, because you're taking properties from other systems already in place, largely from oral language and from the object recognition pathway in the visual system, and you're gearing them towards reading as you become a skilled reader.
And so we know that also the reading entails bringing together several of the senses and skills. In fact, I had read that until the late 19th century, that people traditionally read everything aloud. So they were getting some audio feedback as well as they read, even if they were by themselves in their home. So when you say that changes the brain, then are we talking about changing some of the neurons firing between different areas, the visual cortex and areas responsible for sound and cognition? Is it changing those pathways and those firings, or what are you finding in the fMRIs?
Yeah, so what researchers have shown is a sort of a series of things. These are often from studies that are done in different labs in different populations, but when you put it all together, you see an interesting picture. So going back to the work that's been done in people who are illiterate versus those who are literate, this is the work by Stan DeHaan. What they showed is that the experience of literacy doesn't just change areas maybe in the visual system because you're retraining the visual system to focus on letters and words, not just objects, but also it changes areas in regions that are associated with auditory processing and language processing. So you can think of it as sort of having an effect on the brain, and it's not just in the areas that we necessarily use for reading, but also outside of that. So there's some behavioral research that was a little older suggesting that even if you compare adults who are literate with those who are illiterate, they process shapes differently in the visual system. They may have differences in naming objects. And so the way you can think of this is that when you learn to read, not only do you bring on board all those areas that actually support the reading process, but there may be areas in the brain outside of reading that are also being reorganized as a byproduct of that. And it's something that we don't think about so often because all of the participants typically that we study have undergone this change. Every child who learns to read has undergone this change, and we think of that as kind of the typical brain, where in reality, what's probably going on is that the typical brain is not so typical because it's now the reading brain, and not only has it changed the areas that it needs for reading, but also some other related areas may have undergone some change too, and we don't quite know what those are. Where that's important is when it comes to understanding dyslexia, where we have to be very careful, again, to distinguish our results in neuroscience and ask the question, when we see differences between people with and without dyslexia, are those differences the things that interfere with their reading ability, that cause them to struggle to read? Or are they changes that occurred in the typical readers and those who acquired reading skills, but they haven't occurred in our dyslexic readers because they are not at that same level of reading and their brain hasn't undergone that same sort of reading-induced change based on their experience of being a reader. And
so the terminology, the term dyslexia has often been politicized. How do you use it in your studies? How would you define it?
So the definition for dyslexia that I adhere to is the one that was put out by the International Dyslexia Association in now 2002. I was part of that group that came up with the definition. And it really speaks to the idea that it is a learning disability that's neurobiological in origin. We know, obviously, not just from the brain imaging research, that there are differences in the brains of people with dyslexia, but also from genetic research and so on, that this is something that is neurobiological in origin, and that we think of children and adults with dyslexia as being those who have difficulty with accuracy and fluency of reading. We think of it in terms of text, word level processing. And we know that often these individuals have difficulties with understanding the phonological features of language, particularly at the phoneme level. And we also know that this difficulty in decoding, so not being able to sound out the words, will then eventually interfere with your ability to derive meaning from text. That's a secondary consequence. There are, of course, children who begin with an oral language problem, and that oral language problem may interfere with their reading comprehension. But the way to think about the person who has dyslexia is that if you were to read them a paragraph and ask them to answer questions, they will do fine. But if they have to read the paragraph, you will see that they struggle with accuracy and fluency. And then because of those difficulties, comprehension will also be affected as a consequence of those. So that's how we think about dyslexia. And then the other important part is that you see it despite the child having appropriate instructions, and there are no other obvious explanations to argue why there may be a reading difficulty.
Right, so there's no longer a comprehension versus reading discrepancy that's involved in that definition of dyslexia.
Well, there are different definitions that are out there, of course, and I think the definition I just spoke to is one that is really geared towards the scientific community, the research community. In the educational system, of course, people will use slightly different definitions. And I will say that even in the research community, not everybody exactly uses the same. But there have been prominent arguments about how to define it. The other issue has to do with whether or not you consider IQ in the definition, and from an educational perspective, that's no longer the case. I think that really what people are looking for are the difficulties in single real word reading difficulties with accuracy, and as I said, the comprehension piece is one where yes, they may have impaired comprehension, but in the case of dyslexia, it's thought to be due to the difficulty in decoding the words.
I've heard many people talk about dyslexia being a gift for them. It's allowed them to think differently. Is there any scientific basis to that you're aware of?
This is a very interesting question that has really become very popular, I think, in the last few years. There's a lot of, there's a book on the issue of the dyslexia advantage. There are some interesting TED Talks by people with dyslexia who really feel that their dyslexia made them the person who they are and made them more successful in many ways than they would have been if they hadn't had dyslexia. But the research really is not there to allow us to decide one way or the other, I think. I think the concept is an interesting one because you could have a theoretical model where the kinds of, from the brain perspective, say the areas in the brain that differ in dyslexia, that interfere with, say, phonological processing and decoding and so on, that by not having those, maybe not acquiring reading, there may be some sort of a flip side to that in the brain that it enhances other skills. So the model is out there, but it has to be tested. There are cases in medicine where having a disease protects you from another disease. So that could be a silver lining. I think the excitement about this idea that there are advantages is greater than the data supports. I don't think we have the evidence, but I think we need to do more studies. And I think the thing that I worry about is that parents really need to understand the importance of literacy. And I think it's difficult to learn to read. I think it's really difficult to teach your child to learn to read, particularly in English. And when your child is falling behind, I don't want any parent to feel like, well, if they have dyslexia, that's fine because it's an advantage. And we know about the successful people with dyslexia. I think the people who have dyslexia and have been successful are very impressive. But I worry that they are the exception rather than the rule. And I worry about the child with dyslexia who cries at nighttime, doesn't want to go to school the next morning, says they have stomachache, feels that they're being teased or even bullied by their peers because of their reading difficulties, and essentially are going to school and don't have the benefit the other students do to access of learning knowledge, which is why we go to school, because the door has been closed to them because they don't have the decoding skills they need to be able to get meaning from print. So I think it has to be talked about much more. I think we have to be responsible in terms of how we view these things. And I think it would be good to do more research and have more publications that speak to this issue so that one way or another people aren't confused by it.
Do you find that children that have learned to read, that have struggled previously, have you examined their brains and their scans? Are their brains the same as students who progressed at a quote-unquote normal level?
So that's a good question. So this gets at the brain mechanism of what happens in a child or an adult who has dyslexia, then goes through some sort of maybe tutoring or something, makes gains, and what is the neural correlate of that change? And does it look like does their brain now look like a very typical reader is the question. And I think we don't quite know the answer yet, because we and others have done studies asking what changes in the brain following interventions. And we see changes that support the idea of the increased use of left hemisphere areas that we know are involved in reading, But we also find areas in other parts of the brain that become involved in reading that you wouldn't see necessarily in children who don't struggle to learn to read. And you can think of those as being compensatory. So again, there's sort of a model for this in medicine, where stroke patients following a stroke, when they go through rehabilitation, sometimes it's not possible to regain use of the same brain areas because of the damage from the stroke. And so you see the brain is very plastic, and other brain areas chime in and now take on the job of doing that task. Often it's in the opposite hemisphere. And we do see a little bit of that in our results and the results of my colleagues that speak for this idea that there may be some other brain areas that chime in. When it comes to studying this in the context of typical development, you really also have to study typically developing children more and at over longer durations. People are doing that. It's a little hard to do with brain imaging because it means that the brain scanners need to be around for many years. The people studying the children have to be around for many years. These are longitudinal studies. These are hard to do. But some people are beginning to do them. And once we have these longitudinal studies, we will get a better sense of what is the change that happens in readers, whether they are skilled readers or struggling readers, and how do in fact the changes we see in an intensive tutoring in people with dyslexia essentially recapitulate the ones that we see in typical readers over a longer development.
A big part of our work at Lindamood-Bell involves developing imagery for reading. If somebody's having difficulty with decoding, we try to stimulate imagery of the letters and attach that to the sounds. Does that model fit in with a fMRI study? And if so, where would that show up where would imagery show up, I guess, in the brain?
Yeah, I think that's an interesting question. And this is one of the things that's so interesting about the field that we're in, is that it's so interdisciplinary, and we study the question about areas involved in the brain in the lab, and we design experiments to identify those areas. And then we often are informed by clinical practices or ideas about how you best instruct children to learn to read. And that's really how it's supposed to go, is sort of a two-way street where we inform each other. And there has been a lot of work looking at visual imagery. Steve Carlson at Harvard was the pioneer in doing a lot of that work. And we know which areas in the visual system and parietal cortex are involved in that. So we know, if you just close your eyes and imagine the face of an elephant, and then you try to imagine where you're looking at their ear and you're trying to discern something on their ear. You're doing all that with a lot of visual information that you can see, but you're not even seeing it. And so I think that aspect of teaching children to learn to read has always been very interesting, because we know that it activates brain areas when we know what the signature looks like for that. And I think it really behooves us to have a better understanding of how that strategy manifests in the brain. I don't think we know enough yet. I think people haven't done the exact studies to do that. I think we could hypothesize and infer a lot from the published literature in terms of just visual imagery, what we know. But we are still at the point where we're trying to figure out, frankly, how it is that we organize the brain for reading really at the specific level of the mechanisms, right? We know which brain areas become involved. We know which areas are more involved in established readers than beginning readers. We know they change, but we don't quite know what the mechanism is. And people are doing studies where they're trying to get at those mechanisms, and they involve, for example, studies where you ask, do neurons really get tuned to words? So there's this idea that neurons essentially become favorably inclined to a particular word, and that essentially neurons sort of reflect our dictionary, with some neurons having a preference for one word and not caring about any other words. And so the question would be, how does that tuning come about, and where in the brain does it come about?
Is that like an idiosyncratic lexicon then that someone would have, they've got their favorite words and less favorite words?
Exactly. So the neurons tend to be tuned to a preferred stimulus. So even in our visual system, when something is moving in space, some neurons really like it when it moves from left to right, and others like it when it moves from right to left, and they have their preferences. And it seems it could be true also for words. We also know that there's a mapping in the brain that is sort of a hierarchy of organizations from simple letters to words, that some neurons prefer just the letters and others prefer the full words. So we're just beginning to map all these things out. It was done in sort of simpler objects, and a lot of the people who focused on object recognition, and some of this work was done in animal models, and have now transitioned to the human brain with brain imaging, and they're trying to understand how it is that our neurons become organized for recognizing these words. And that needs to be done in the context of things like visual imagery, and it hasn't been done yet.
So what are you working on currently? What studies do you have in the hopper?
So at the moment, we have an interest in children who don't just struggle with reading, but also with arithmetic. And we have a grant from the National Institutes of Health and another one from the National Science Foundation, where we use a tutoring intervention from Lindamood-Bell, and we address reading difficulties and math difficulties. We began our work by looking at children who only had reading difficulties, and we have since expanded it to look at children who have reading and math difficulties. They are what often is referred to as comorbid. They have both math disability and reading disability. And now more recently, we are including children who only have math disability but have typical reading skills. And so with that, we're trying to look at the whole spectrum. And the reason why we're doing this is this. It could be that some of the same skills that you need to become a skilled reader also make you good at arithmetic. That's been an ongoing question in cognitive science, and it's interesting because if it's true, then it could account for why we see more children with math difficulty in the dyslexic population than in the non-dyslexic population. The idea that there's a more general skill that is needed for both, and it could be we focused more on the reading problem because reading is the gateway to learning. And it may have seemed in the past that math is not quite as important because it's just sort of focused on math. But I think as the research has moved forward, the importance of arithmetic is being recognized, and the importance of helping children who struggle with arithmetic is being recognized. So the imaging can provide a way to shed light onto this idea of whether we see differences for math processing as we do for reading. And do we see them in children with dyslexia or children with dyslexia and dyscalculia combined? And we got into this question by finding, somewhat surprisingly, that our children with dyslexia, when they solved math tasks, even though they were able to do them, used different brain areas to do it. So this is an example where brain imaging can provide information that is new and shed light sort of what's going on under the hood, so to speak, where these children behaviorally, if you had looked at them, didn't seem to behave any different. They were able to solve the math difficulties, but we discovered that they do it with different brain areas. So children with dyslexia use different brain areas than those who didn't have dyslexia. And that sort of did speak to some other evidence that's out there that children have difficulties in arithmetic when they have dyslexia, not just all aspects of arithmetic, but particularly things like small number addition and multiplication, which are thought to be subserved by processes that involve retrieval from memory, phonological retrieval from sort of lookup tables, because when you do things like 2 plus 4, you use a different cognitive mechanism than when you're doing 4 minus 2. Sort of very broadly speaking, one is a left hemisphere task and the other one is a right hemisphere task.
Is that why we had to memorize the tables of multiplication and addition tables, so that it's more of a rote memory than it is actually thinking it through?
Exactly. You pull up that information, whereas when you're doing subtraction and divisions, you have to do the computational, and you do that in different brain areas. So we're studying this, sort of asking multiple questions. We're interested in the brain bases for these different kinds of arithmetic tasks. We're interested in how they differ in children with dyslexia and in children with dyslexia and dyscalculia and children with just dyscalculia. And we're using the tutoring of both reading and math as a way to probe the system. So it's wonderful in that the children who are in these studies are receiving an intervention to help them with their difficulties. And we use the intervention as a way to understand what changes in these brain systems as they make gains in reading and arithmetic, as a way to help us understand what is the best model to explain dyscalculia, dyslexia, and their coexistence.
And so are you doing several scans, like a before and a pre-intervention and post-intervention?
Yes, these studies are quite involved for our volunteers and for us as a research team, that children come in at multiple time points. They come in prior to the intervention and then following the intervention, and then they receive both reading and math interventions. So then they come in for a third time, because halfway through the study we switch from reading to math or from math to reading.
So it seems that reading and math almost have parallel processes with the decoding, comprehension. Is that akin to the calculation and computation parts of mathematics?
It's an interesting question. So I think what we can say is that some of the skills that we use for addition and multiplication share brain regions with reading. So, for example, some researchers have shown how areas that are involved in phonological processing are also involved in multiplication. And it seems that when it comes to subtraction and division, that shifts to the right hemisphere and doesn't seem to have so much in common with phonemic awareness and decoding.
Interesting.
And then you think about if you overlay any of these difficulties in arithmetic or reading on top of that, then how does that manifest in the brain?
Well, if people wanted to kind of follow your research, where are some good websites or areas that they could look at to look into more of your work?
Well, we have our own website, which describes the studies that we're involved in. It's if you Google the Center for the Study of Learning at Georgetown University or CSL at Georgetown University, you'll find a description of our studies, and you will see what kind of studies we're recruiting for. You will also see that we have other research questions. For example, we're interested in the moment. We're looking at also bilingual people. You know, we think of the importance of experience, and if you have a bilingual experience, what does that do to the reading brain? We also are interested in how the brain is organized for reading when you read in different in languages that have different orthographic depth. So particularly we're contrasting Spanish and English right now. And you'll see some of the other work that we've done in the past, for example, focused on, again, bilingualism or people who are bilingual in a sign language versus a spoken language and so on. So that's a good place to come and see the work that we do. Well,
I think we'll wrap up. I really appreciate your time today and some very fascinating work that you're doing. Thank you so much for being on the podcast.
Thank you for having me, and thank you for your excellent questions.
And thank you for listening to the Lindamood-Bell radio podcast. I hope you listen to more episodes, and if you enjoyed this, please subscribe. Follow Lindamood-Bell on Instagram, Facebook, and Twitter at Lindamood-Bell.